Loud. So should I like have it like here? It's okay, I think.
I think it's okay. All right. So, if you hold it, it'll be on, and then if you hold it, it'll be.
When you ask a question,
Hang on. Can you see?
it doesn't do anything.
So hi. Hello. Okay. That's fine.
Yes.
So when people
Great.
see this video later on, they will hear your question, they will see that you're the one.
So my name is Marek Hrus, and I come to you from Czech Republic, as many of you already know. We've met before, right? And we are from the Department of Cybernetics, University of West Bohemia, in a lovely city of Pilsen, the birthplace of the modern beer, yeah? And today I'm gonna talk about vision mostly, computer vision, and how it connects to sign language, since this is the project we are working on during the workshop. And let me take you a little bit through the history. I mean, yesterday we had a nice lecture from Florian Metze, and he told you a lot of stuff that I'll also have on my slides, so I'll just skip through them fast. But I know that also students need to be reminded about the basics so that they can follow, right? So first of all, image classification and convolutions for the win. When I was a student, we were doing stuff with vision that was mostly handling individual pixels and comparing them, trying to build some shapes and handcrafting features so that the standard classification methods can cope with the problem. And it was really tedious because you just worked for several weeks on one image, or two images. Then here comes your validation set, right? And everything fails because the sun was shining from the other side or whatever. And in 2012, I was introduced to a paper about AlexNet, which was really, back then I could not really see where all this will lead. And the paper introduced the convolutional neural networks. We knew about convolutions back then because it's old theory. And everybody is learning about it in really early years of their studies. So that was nothing new, but we did not know about how to use it in a machine learning setup. And also, I have this slide on the data, and the modern deep learning stuff is nothing without data, and it has been shown that we can scale the systems, and if you even now know that if you don't have enough data, you cannot train your neural network, right? So this is a slide about the ImageNet dataset that was presented back in 2011, and there was a competition connected with it, and people are doing image classification. And just the last line is that the best handcrafted features of that day, which were SIFT, Scale Invariant Feature Transform. It's a very lovely algorithm, and if you pursue computer vision, I would really suggest that you look into it and see how it was done in the olden days. And then there were some, Fisher vectors on top of it, so some dimension reduction and so on. And just, use SVM as your classificator, support vector machine. And it was actually quite good because we got to one accuracy of 50% on this data set of 1,000 classes. So, and even now, if you go to industry, it's fine to use simple computer vision stuff and methods if you have a simple task, which is well defined, the conditions are perfect, lighting is always controlled, and so on. So that's what I'm telling my students, don't think that I will just throw, a network on the problem and everything's done, right? Sometimes you can solve it more robustly without a neural network. And so in 2012, the AlexNet comes out. And back then, the image on top is very important. You see, maybe there are two branches of the net. It has nothing to do with the method by itself. It was just the computation was so bad back then that they needed to split the architecture on two GPUs to be able to train it. And back then, 2012, I don't know who remembers, but the GPUs were not that strong as now. So it was a big achievement because actually the method was introduced, as you heard yesterday, in 80s, right? So it was resurrected, and just, they say, let's give it one more try, one more shot, and see what we can do with it. There were some interesting findings also that before that, everyone was using fully connected layers with sigmoid activation function. So they found out that actually ReLU, or the linear unit, it works quite well. It has good properties regarding the learning. It has like, I mean, the gradient is practically a constant. There's just one tiny problem at the 0 where it is not defined, but you can, you know, work around this. Yeah, so, and they achieved top 1 accuracy of 63%. So back then it was like they were, you know, fighting about 0.5% of the accuracy, and suddenly this giant leap comes just by using a new method, completely new method. And before that, I actually the mainstream idea, let's say, was that neural networks, like, they will never work. It was just maybe, you know, 1 year before it was like, yeah, I mean, they can do stuff, but we don't want to use it. And when I talk with my professors, they say, because, you know, the method is fine, but we cannot like look into it, and we cannot like just turn one knob and just, you know, solve the problem. So we don't know what's happening inside. And that's true even now, even though the explainability and interpretability of neural networks is a big topic now, and it's actually very interesting, and OpenAI did some good stuff with it. So yeah, but still the problem is there, but the results are so good that you just don't care now. Or I think many of you do not care when they are using the neural nets. And there are some implications, some, let's say, emergent properties. And yesterday, Florian, you saw the image up there. Those are the kernels from the first layer of the AlexNet. And you can see they are really like, they resemble the handcrafted filters that we were using before. So for me, this is like interesting also because it tells us something perhaps about ourselves. Like, you know, there are debates like how did humans come to be and so on. And we can see that perhaps it is hidden in the nature and in the reality itself that we need some kind of general, you know, processors of the reality to be able to understand it. And the machine has learned it by itself without any a priori knowledge from us, just from the data. So then, yeah, then this is maybe argument against, you know, some need of intelligent design. But again, it may be the other way around also. Maybe the world was designed intelligently and we are just emergent property of the reality, right? And there are some more interesting stuff because the image classification is a problem where you assign one class to the image. But generally, I don't think that people work this way, right? Even because you have to choose if there is more objects in the image, which one is the one that you want to classify. For example, here, this image, the network thought is this a convertible, but the human thought, no, that's a grill, so it's the front of the car. So actually, the evaluation said, yeah, the network doesn't work on this image, but in reality, is it true? I don't know. The same, this image tells us something about the details. Like, the network just said is a mushroom, but actually it's agaric. Who knows what it is, right? It's a type of the mushroom that's on the image, yeah. But it's a mushroom, so for me, good. And this is a picture, of a Dalmatine in front of cherries. So this is maybe one example where I think that the human experience come into place, because I think no one would say that this is an image of cherries, right? This is an image of Dalmatine. Yeah, but somehow the human decided, the network decided this is a cherry. So this is another example here, because then they said, okay, so when we have a linear classification layer at the end of the network, so the space which is modeled in front of the last layer should have some interesting properties, like the images that are in one class should be close together. And this is a problem of also image retrieval when you wanna get some image that is close to your query. And they just tried it, like let's just take some image and give me the closest images meaning Euclidean distance, computation of the distance, in the penultimate layer of the network. And suddenly they found out, yeah, that there is something in there, because the images do not look syntactically very similar, meaning when comparing pixel to pixel, you would actually get huge distances, but somehow the semantics of the image was encoded by the network. And this is an interesting emergent property that is used now in every domain. So this is something I wanted to add on top of yesterday's talk. And, you know, as time went, it actually began to run exponentially fast, let's say, because just, you know, in 2 years, Google, they proposed VGG, which achieved another big leap, 74% top one accuracy. And there was just the idea of, hey, if you go deeper into your network, the network actually sees more of the input. It's called receptive field. Yeah, because when you stack convolutions on top of each other, you just see a bigger part of the picture or the image. And so they said, let's just try some small kernels, like 3 by 3 instead of 11 by 11, which were in the Alexander network. And suddenly, with these minor tweaks in the architecture, they were able to achieve this accuracy. So yeah, then this tells us something that it's somehow important, like how you build your network. And also they found out, or researchers found out that, but we cannot go deep, you know. So if we go too deep, we get this problem of vanishing or exploding gradients, depends on which one happens first. And it was really, you know, it was really sad, because we thought that, oh, we just, you know, stack more layers there and it'll work. But it did not happen. And you can see in this image that this is the example that if you have 18 layers, you get actually better scores than when you have 34 layers. So then 2015, ResNet or residual networks come into play. You can see in the diagram, the whole idea, probably many of you already know, is just to skip some layers, and the gradient can actually flow through the skip connection and not be zeroed out or not explode. So, and then you get better results, and now you know maybe the best or the most used ResNet has 50 layers. You can go 101, and I don't think people use more depth, but in some papers they go like extreme and they have even 1,000 layers, and it still works. It's and the network still learns. Okay, and because we have this, now we have these architectures and we have these emergent properties. So the question was like, since the network seems to be modeling some semantic space, is it useful in detection? So again, we need some datasets for this, and datasets is for detection are harder to build, because people have to like by hand, they have to, you know, say there's a dog, there's a cat, and there's a duck or whatever, and draw the bounding box around it. And in the perfect world, even, you know, draw the mask of the object for semantic segmentation. And these are like the, let's say, Pascal VOC was like the first data set that was used for the detection, and it had only 10,000 images. Back then it was like, whoa, this is like very, very large number. But we know today that it's nothing for this for the network. And then the most cited data set now is Microsoft's Coco. And it has many tasks in it, if you do not know. So it's it can do object segmentation. Also, you know, you can use it for classification, but there are also poses and so on. So it has around 200,000 labeled images with 1.5 million object instances. There are only like 80 object categories. So when compared to ImageNet, which is actually 21,000, but only thousands are used for the evaluation usually. So 80 is, yeah, it's not a lot. And then we have 91 stuff categories. And so objects or things, sometimes called, are things that actually, you know, is reasonable for them to have a bounding box. It's like an instance of an object, like this cat, dog, duck, car, or motorbike, or whatever. And then you maybe wonder what is stuff. Well, stuff's the stuff that cannot have a bounding box, or it's not, you know, it's not like you can have a bounding box around everything, yeah, but it does not tell you much. And those stuff is like, you know, sky or sea or, you know, a desert, something that, yeah, does not have an instance, even pavement, you know, road, something like, imagine stuff like, I wanted to say things, no, stuff like this. So the terminology needs to be there, right? Things and stuff. And this is used for panoptic segmentation. I will show you a little bit about it on next slides. And there is also captions there. So, for example, my student Thomas used it for his diploma thesis for image captioning. So, yeah, it's I mean, it's a nice data set overall. And the newest one for that is being used is objects 365. So accidentally add the same number of days in a year, which is like 2 million images and 30 million bounding boxes. So if you want to go, you know, like further in the number of objects you have, you go for the objects 365. And you know, in the year that ResNet came out, also like the first, let's say, modern detector came out, faster RCNN. And here is just the general idea about the model. So you actually use your convolution layers, and you can reuse, and nowadays you do it like that, you reuse the already trained model that was trained on a ImageNet, and it can be ResNet or whatever. ResNet is the mostly used. You can go MobileNet if you need performance. MobileNet is like a lightweighted architecture that has good performance, but also not so many flops. There are lots of tricks inside of it. So you use your convolution layers, you go up until to some, you know, last or penultimate feature map, and you do your regional proposal network. So the regional proposal network is actually just looking for the objects in general. So it's a binary classification system that just tells you, like, I think that there is something, you know, in this box, and then you send the box into your classifier. So in the next images, you can see that on top of the feature maps, you have some sliding windows. So of course it's implemented as a convolution, and you take, you know, features from this and put it into your intermediate layer. That is a fully connected layer with, let's say, in the original work it was 256 dimensions, and then you have two heads, and this is what we in Vision call then heads, because each head can have you know, its own task to solve. And in this case, one head it just classifies whether there is something in the window or not. So it's a binary classification, and the other head is regressing the position of the box. So when I was before this, you know, I was doing my my PhD, and I finished, you know, in 2013. My PhD thesis did not involve any neural networks, and thanks God for that, because just 1 year later, and my work was deprecated, you know, so lucky me. But I was thinking, like, okay, so now we can do classification. And as you know, when you classify, you just add your classification layer that has as many neurons as you have number of classes, and you can just, you know, run it. But what about objects? Because you have, in each image, there's a different number of objects, right? And you cannot dynamically change the number of neurons during training, during inference, or, I mean, technically you can code it with dynamical models, you can, but I don't think it'll work, yeah? So how to make it like constant? How to find something that is constant in the task? And they, in faster CNN, they came with these anchor boxes. So that just say, let's populate the image, yeah, with some boxes. We will have a constant number of them. And then we will actually predict for each of these boxes whether something's inside and how we should change the size and positioning of the box. So that is happening in those two heads, right? So you have K anchor boxes for each position, and they are actually different in sizes and aspect ratios. So they use like 3 different aspect ratios for each size, and that gives you the number K, how many anchor boxes are in one position. And for each position, let's say we have 6 boxes, so you have 12 neurons. For each box, you have either something's in that box or not. It's a binary classification, but not in the sense that you would have, 1 neuron with sigmoid, but you have softmax and 2 neurons. And the other one is for the regression. So we just say like, hey, we need to move you a little bit to the left and up, and you need to get a little bit wider, let's say. So that's actually regressing the position and the size of the box. And then since you have, you normalize your input resolution, then you have your constant number of boxes in the image, and suddenly you can fix your architecture and just predict it without any problem. And this method actually gave us very good results. And it has been shown that the backbone, we called it backbone back then, which is trained as a classification task, can be reused for this detection task also. So the features that the backbone is producing are actually semantically interesting, also for the detection. And from there on, no one was trying to train the network from scratch, and everybody was just using these pre-trained models. So this was like a step before the now foundation models, right? So yeah, it was a backbone model, which is actually interesting from also biological point of view. I was talking with one professor who was visiting Pilsen, and he was doing neurobiology, and they were running these experiments, I think, on ferrets. It was actually funny because I didn't know that. Sorry? There's a question. Just raise your hand. Yeah. Okay, go on.
If you have a constant number of boxes, how can you have a variable number of objects in the images?
Sorry, of what?
If you have a constant number of boxes,
Yeah.
6, that you're trying to move around, how can you end up with only classifying 2 objects in the image rather than the boxes sort of landing at some random part of the image?
No. So yeah, let me maybe be more detailed. So for each of the position of the sliding boxes, you have K anchor boxes, and you just you use your one head to tell you whether there is something inside the anchor box or not. So if you have just 2 objects, so a lot of boxes will say like, there is nothing in me, there is nothing in me, there is nothing in me. And then you move your sliding window to the next position, and you use the same weights because you want to be like invariant to translation, let's say, and scale. So you just move your sliding box and do the classification for all the anchor boxes again. So like 99% of the classifications will be like, there is nothing inside of the box, and just the 1% will tell you for the 2 objects. Let's say, yeah, there's something. Yeah, was it answered? Okay, thank you. So I don't know, maybe I will repeat the question was like, how can I, classify just 2 images when I have like thousands of anchor boxes? Yeah. So the idea is that you have this classifier, and it tells you whether there is something in the box or not. Okay, and so back to the ferret problem, because I spoke to the professor, and I did not know. Yeah, it was a little bit embarrassing, but I did not know he was actually author of the research I was trying to explain to him. So, and I was telling him like, I read this interesting research about ferrets that they had damaged their vision center in the brain, and then they were able to retrain the hearing center of the brain to process the visual signals, and the brain actually did learn to process this signal from the eyes again. And he said, Well, actually, we heard the ferrets. They were not like heard before. We had to actually heard their brain so that we damaged it. So I was like, okay, so it was you. And he started to talk about neuroplasticity and this stuff. So yeah, but in the end, it was actually, he was really, you know, like easygoing. So he forgave me that I did not know, and we had a really good conversation. So this is something because I told him about this backbone networks, and he was interested in this because it showed some analogy with this, like the structures in the brain, even though they are specialized, they can adapt to different tasks. So this is something analogous maybe to the backbone network that, yeah, the brain can process the signal and just, you know, pre-process it for different specialized centers. And they can even exchange the function if you made it. Okay, and so this is the, let's say, the first network that was used. You can see that on Coco it had a mean average precision of 42.7, and there's the at 0.5, which means like, you know, like if not precisely, but let's pretend it's a 50% overlap of your detected box and the ground truth box. And 44 seems a low number, but actually it's when you are using it in practice, it's good enough. So you can do some nice applications with this. Okay, and then only a few months later, SSD comes out, which is a detector that does not use this, let's say, two-stage prediction of the object. So it does not actually first propose the regions because in the I haven't finished. Like the last thing is that when you get your region, you just take it, you just reshape it into a rectangle, and you just put it into your convolutional neural network for classification. Yeah, so it's two-stage. First, you get the boxes, and then you put it into your classification network, and it decides what's in the box. And SSD said, well, what if we do it in one step? So what if instead of having to decide whether there is something in the box or nothing, we will decide whether there's nothing or some class. So they just classify directly, and they showed it works. And they also use like this multi-scale approach, because in the faster RCN, they just took the last feature map. And as I was saying before, as you go deeper and deeper in the network, you are actually observing a larger and larger part of your input. And this tells us something about the scale of the objects. So as you go deeper, you are actually losing the detail, right? And you are just looking at the image semantically. And in the classification network, they wanted to do this because they want to compress the semantic information into small space. Yeah, but then you have problems in detection tasks because you can lose the small objects. So they just say, okay, we will not just use, you know, the last layer, but we will use like, you know, some earlier feature maps, and they even put some like 2 feature maps on top of the back then it was VGG16, you can see. So yeah, they used VGG16. They used only, I think, 13 layers. Yeah, and then they, you know, did the same stuff with the anchor boxes, although they called them default boxes just to, you know, confuse us, but they are the same. Okay, and then they classify directly into a class, or as we like to call it in Pilsen, a garbage class, which is the class that, you know, takes in everything into it that is not important for the task. Yeah, and they have like 74 MAP, and they run 59 FPS, which was a big deal back then because you could do real-time detection. Okay. And here is a little bit about like learning and inference. So how do you exactly, you know, tell the anchor box that there is something inside of you? So we just compute intersection over union, which is this. I have the graphics there. You just take, you know, the intersection of the bounding boxes, and you divide it by their union. So in an ideal detection would have IOV of you know, of 1. And of course, there is like the problem that there are too many negative boxes. Yeah, because if there are just, you know, 2 objects and you have like thousands of anchor boxes, just maybe, you know, 30 of them tells you that, hey, I have sufficient overlap with the ground truth box and I can learn for the positive class. So they have to, you know, tweak it a little bit, and they just take a constant number of negative examples. Yeah. And then the last function is just the sum of the classification and regression error. So we have for classification, you have categorical cross entropy, and for regression, you just use smooth L1 score. So L1 score, you know, would be just this linear function, but the smooth one tells you that if you go close to 0, just make it, you know, smooth in the sense that there will be L2 norm. Yeah. And the problem then is that during inference, you usually detect one object multiple times because you have multiple anchor boxes in the same position and you have to do a lot of post-processing. And this was like, sometimes you did not get good results. So you have to, you know, tweak your post-processing parameters to get good results, but then it fails. And yeah, so this is the engineering stuff you have to do on top of it, because the scientist, the PhD, can just say, okay, my paper is like done, it's well cited, and I'm fine. I go to the next thing. Yeah, but then the poor souls in the industry have to really use it, and they find out that we have to like set thousands of parameters to make it work. Yeah, and that's pretty normal. So yeah, when you are going to decide what you want to do after your master's, you know, there are 2 ways to go. Yeah, either you will be in theory and develop the basic ideas, or you go into the industry and you try to, you know, play with your parameters and hyperparameters and all this stuff. Yeah, so decide wisely. Okay, and what about the next big leap? So transformers came in 2017. Attention is all you need, and we all know this paper, or many of us know, and the ones who don't know definitely read the paper, because, you know, I was used to was used to say like, well, it was just few years ago, and today I look at the date and it's 7 years, so it's not that few years ago. It starts to be long time ago. But anyhow, it was like, if you remember the timeline, 2012, modern convolutional neural networks are discovered or described, and 5 years after that, transformers are born. And now it's 7 years, and no more new architectures for us. So I'm looking at the young guys in the audience and gals, let's say. You should come up very quickly with a new, with the new architecture that will defeat transformers, so that, the scientific field can move on in a proper way, And so this is actually transformers. I just, will pick some main ideas that I like, which is the introduction of attention mechanism. It was used before in recurrent neural networks, but now it's used like exclusively, and the model removes the state. And that is something that can divide people into two groups. Some I'm a fan of a state, actually. I mean state, not like in geographical state, but state in neural networks, because I think that we as humans, I hope that we have some internal states that we are, using to define ourselves, and we are not just machines processing, sequences of data running into their brain. So, but transformer showed me that, yeah, you don't need state, and maybe you are just some kind of really large multimodal transformer, and maybe you are just, going through the world processing stuff with attention, and you do not actually model your internal state. But still, I refuse to, to believe this. And and then you have this encoder part, which is that one from your side on the left. And it encodes the inputs, and the attention mechanism is like telling each input like, hey, how are you related to the other inputs? I like to interpret it like you have this key, query, and value vectors. And the query vector is something like, hey, guys, I have these questions too, because, you know, I by myself, I'm something, but in context with you, I'll change, right? It's the same with people. People, when they are alone at home, are behaving a little bit different than when they go to a party, right? So the query is like, hey guys, I have these questions for you. I need to answer so that I know better who I am, yeah? And the keys are like the answers to these questions. And also I can provide you with, if you ask me or queries, I will give you these answers. So this is for me, the main idea of self-attention, that the vectors are asking the other vectors, including themselves, some interesting questions. For example, in Slavic languages, the words you need to change a little bit because they have a gender. So according to the gender, you have to change the word. So, but the word by itself does not know the gender because it can be a verb. So it has to ask a noun. Hey, are you a girl or are you a boy or are you a it or whatever? Are you a they? And they, you know, they are awaiting the answer so that they know how they should interpret themselves. So this is the query and key values vectors, and then there is the value vector, which is like going through the model and you know, aggregating the information. And and then you have this decoder, which is you know, very similar to encoder. You just have this cross attention module inside, which takes the values or the vectors of key and value from the encoder, and the query stays in the decoder. So actually there, the decoder is asking like, hey, I have these questions, encoder, what are your answers? And the encoder tells him, okay, these are my answers to your questions. And you have a masked multi-head attention down there. The masked part is just for the autoregressive versions of the decoder. So this is used when you want to do, for example, translation, as was demonstrated in the original paper, or when you want to do, you know, some text generation. So you decode, you know, a word by word or token by token, and then you get the information about what was already decoded, so that you know better what to decode as the next vector. So this means autoregressively. So you just take your output and bring it back to your input and proceed with generating other outputs. But in Vision, we do not use this. We have our non-autoregressive decoders, meaning that beforehand, we know how many tokens or how many vectors will be decoded. And they, through the training, they can know about each other. Yeah, so they do not have to wait, you know, for their turn to be decoded. No, they just go. And this was used in the first Vision transformer model, which is called, I think Florian said DETR, which would be like American or English pronunciation. We say DETR in Czech, you know. Sounds like, for me, it sounds better. Means, yeah, DETR. And detection transformer. Yeah, like it's a better. DETR is like, is it detour or what? No, DETR. Yeah, very strict. And Florian is German, so I don't know why he did not use the German pronunciation, DETR. So it's detection transformer, DETR, right? And what they did was actually they took a backbone again. So back then, remember, it was called backbone, which was ResNet, usually ResNet 50. And they got their features from the last layer. And then they add 2D positional encoding. That is something that in the images, you know, it's mostly used is this 2D encoding. And they just take these features, add the positional encoding to them, put them in a transformer encoder. They encode these features. And then they use a non-autoregressive decoder to produce the objects. Okay. And so the positional encoding is interesting because you have to have actually even a number of dimensions so that you can split it in half, because the first half of the positional encoding is encoding the X position, and the other half is encoding the Y position. So yeah, so when we were trying to use it in 3D, we had a tiny problem with it, because you know that people from deep learning like their all even, number of dimensions, and usually power of 2s for some reason. There are some exceptions, like 768 dimensional transformers, right, in their default configuration. So yeah, those are the main ideas. And then after this, you have, you have, again, you need something constant. So they said, because if you would use autoregressive decoders, you can have your dynamic number of objects, but how do you decide which objects should be decoded first, right? In some cases, it might be useful if you have some hierarchy in your input. Like, for example, I'm detecting I don't know, a road. On that road is a car. In that car is a driver. Then that can make sense, even though I haven't seen any research on this. So maybe there's something that can be explored by someone, I mean, who is younger and has the time for it. But in this stuff, what you do is actually take your output of your decoder, so your decoded vector, and you just use some classification hat and some regression hat. Again, so it's the same as in faster RCNN. And you just, classify it either as one of the classes or as no object. So it's similar to the SSD approach. So you have n classes, so you just add one more class, which tells you there is nothing inside. And they say, let's do 100 boxes per image. It was actually some statistical, computation on the COCO data set, and they found out like there is never ever going to be more than 100 objects in my image. So you just set your object queries as the input of your decoder to be like 100 of learnable vectors. So these are initiated randomly. And as you go, you just, learn. It's the same principle as in class token when you do your language models, yeah? So these are learned object queries. And what they say is actually like there's this hypothesis that after this, we do not need to do any post-processing of it, because the decoder has self-attention in it. So the objects, the queries can actually, speak to each other during the training and then inference, and they can tell each other like, hey, I see a bird. Yeah, but man, you are missing the beak. Okay, so you go. I'll stay behind. And the model actually solves this, explicitly inside of itself. And there is, again, the redundancy that you have 100 objects that could be detected, but usually there is like up to 5 in a normal situation. But then again, if you go to industry and you have some problems of detection of, I don't know, transformers on your chip, and you can scratch your head like, why is it detecting only the first 100, right? Yeah, because you haven't paid attention. You need to raise the number of your object queries. And furthermore, you should fine-tune, right? And there are some, again, some implications of this. Because now, when we have convolutional neural networks, and we want to test, like, what is the network actually looking at, you have to have some, TDS algorithms like GradCam or whatever that is computing some kind of flow of gradients through the image, and it takes a lot of time and so on. But in Transformer, you have the attention, right? So you just check, like, in this image of cows, it's from the original paper. It's not that I would prefer cows, but you just click here, like, in this point, and ask, like, what is the attention of this point, when we look at the input, and it just gives you these results. So actually, you see that the decoded objects actually attend to some interesting information in the inputs, and this, of course, gave the authors the idea, the same idea that was done before. Convolutions, they model the image as some into some semantic space. So it seems that the transformer is doing the same and even better. So let's use it for segmentation. And so this was like panoptic segmentation almost for free. So panoptic meaning we are, it's like a superset of semantic segmentation. In semantic segmentation, you just assign each pixel a class, and in panoptic you add the stuff thing into it. So the things that cannot have a bounding box. So you just take your debtor and you provide it with your decoded objects and attention maps for these objects, and just run a simple FPN style CNN. FPN meaning feature pyramid network, which is a topic on its own. I'm not going into it. So, but if you are interested in computer vision, you should definitely look up feature pyramid networks. And you see you add intermediate, ResNet features into it, and then you need a dataset to fine-tune your masks on. They used the COCO dataset, and you get your panoptic segmentation, and it works really well. And yeah, so nowadays it seems that transformers are the dominant force in vision. Although, as Florian mentioned yesterday, and I maybe asked about it also, that they needed a lot more data to defeat convolutional neural networks in classification approach. But that is actually, on one hand, a bad thing because you need more data, but on the other hand, is a good thing because you know that you have capacity in the model to be able to learn more difficult problems. Yeah. So, and this is another interesting result from the paper, because then they actually asked like, okay, so I have these 100 slots for my objects, and I will statistically compute what are they looking for. And in this image, it's just an example where you can see that the queries actually specialize on position and shape of the objects that they are detecting. So always the point is in the center of the box that was detected by individual query vectors, and the color is just let's say the size or shape of the box. So you can see that each of the queries is actually specializing at some kind of position and shapes of the objects. So this is interesting property also. Yeah, and there is the question about, okay, since I have my 100 hypothesis of where I can detect the object, how should I build my loss? So they are using the Hungarian loss. So it's a Hungarian algorithm, aka linear sum assignment from SciPy. We just find, the lowest cost of assigning something to something else. So you build a cost matrix, and you have your 100 hypothesis, and then you have your number of GT boxes, and you just compute the optimal assignment. So we are finding an assignment of your prediction to the ground truth object that produces the lowest cost, and the cost is computed from generalized IOU. You have a reference there to the paper. The generalized IOU is important because when you are computing intersection over union and the boxes do not overlap, you just get a 0, But as you get closer, you would like, your loss to get smaller and smaller. So that is what generalized IOU does. So when the boxes do not overlap, they still give you like some kind of measure of closeness to your ground truth. So that is interesting. Okay. And yeah, and then actually after this detection model, the vision transformer comes. And yeah, it has been discussed yesterday, but so just a reminder, the paper and images were 16 by 16 words, which is a clever play on it, because you just divide your image into 16 by 16 into a 16 by 16 grid, which is like demonstrated here, just 3 by 3, but we have different types. You have that you can split your image into, but each time you have to train your new model. Yeah, and the idea is simple, like these patches will serve as our words, and we will put it into a linear projection layer, which is like, you know, an embedding, because yeah, an embedding is nothing more than a fully connected network. But in this case, we do not use these one-hot sparse representations, but we have dense representations. And then we add this class token into it, so that is very familiar for everyone who is using vision transformers or even, you know, text transformers to classify, for example, the text into domains and so on. And yeah, and you just do the encoder part. You do not need to decode anything. And then you just have this multi-layer perceptron hat on top of the class token, which ends up with a convolution, with a classification layer that has as many neurons as you have classes. So this is really simple. And yeah, and then they showed that well, we can be as good as ResNet on ImageNet, and we can even defeat it if we use like 300 million more images. Yeah. So if you know, I have it on the slide, ImageNet has like 14 million images. So we need like, what, 20 times more data to be able to beat convolutional neural networks. Yeah, but as I said before, it's not just a bad thing, it's also a good thing, right? So what's interesting there? I mean, me as a computer scientist who was, you know, working his whole adult life on like these pixel adjustment things, flattening the image was like a dirty word to me, you know. And suddenly they come up with this and they say like, oh, just flatten the image into a vector because you need vectors in your input, and it'll work. You just need these 300 million images. I was actually, because this is what I will advise to read appendixes of papers, read footnotes, because for the first year I was really angry with it, and I was like, why don't they use convolutions to pre-process the patches, right? Because it can give you some semantic information. And if you look in the appendix, they tried it and it was worse. But still, you know, I'm like, as I'm becoming older, more conservative, I just cling to the old ideas. And I was like, oh, maybe they did it wrong because they trained a shallow convolutional network, just I think 3 layers from scratch and end to end. So maybe if you took like first 3 layers of your ResNet and just, you know, freeze it, I don't know, but I think they tried a lot of stuff. And this, for me, this was like the implication of why they need so many data. Because if you move, you know, your patch just 1 pixel lower, your whole vector changes, and dramatically. Really, it can be orthogonal to your previous representation, right? So that's why they need so many data to be able to process it. But maybe then they, you know, the model has this capacity to learn the stuff, so maybe it's beneficial for the transformer. But if you look at language, it doesn't happen like that, right? Yeah.
Reminds me of the fully connected versus convolutional classification.
Exactly. It's like a step back, right?
So I see why this.
Okay, yeah. I mean, there's this theory that if you have like enough computational, you know, power and enough data, you just use fully connected layers and it'll learn. But yeah, I don't know. So maybe we are, again, you know, maybe our children will look at us like, you know, cavemen. What were they trying to do? Like some, you know, handcrafted architectures. Yeah, and we will be very sad, I think. Yeah, but who knows? Who knows what will come? As yesterday, Florian mentioned something similar, like the scale will always beat the method, right? So maybe there's some truth in it. Yeah. Okay. So and as I mentioned there is much less inductive bias than CNNs, because yeah, CNNs has this equivariancy towards translation. So no matter where your object is in the image, the convolution will always peak at the position, no matter where it is. But this is not, available for the transformer. So it has to learn all the objects in all the positions and so on. Because you even add, your positional encoding into it. So this patch, if it moves to another position, it will have another representation. So we really need to learn like all the positions of the patches. But even though it has more parameters than CNN, it has larger throughput of images, meaning it's faster. Because you do not need to compute huge feature maps and so on. So yeah, that's again, that's a nice property. Okay, so that's the vision transformers, and this is something that has been done, 4 years ago or 3 years ago, let's say, is distillation of information. So as a student, I was afraid of this word, like distillation of information. It seems like too much. I don't want to, learn about the next topic, and I have my convolutions. I need to, work on that. But as a senior, I just, read the paper and I was like, okay, so this is it's quite easy to understand. So the main idea about distillation is that we have a general large model which is able to understand, a lot of topics, but you need some lightweight architecture to perform as well. And in distillation theory, it has been shown that your distilled models actually can work better than your previous models. And back then, the idea was like, the best performing models are very large convolutional neural networks, but the transformers have this nice property of larger throughput. So let's just distill the information from the convolution, because what it enables you to do, you train your convolution on, let's say, 1 million or 300 million images, labeled images, and then you don't want to get another like 300 million labeled images. So you just let the convolutional neural network do the labeling for you, right? It's just a guess, but the network is like trained well, so the guess should be pretty good. So then you can have like almost unlimited number of training data, right? So what they do is actually they use then the convolution in the DATE paper, or I don't know how you would pronounce it in here. DATE for us, Czechs. And you just, add, so you have your class token, here's closer. So you have your class token as in vision transformer, and you add another token, which you called distillation token. And what you do with it is like, I will, if I have a class, then I will use the class token, but and also let's say the prediction from your convolutional neural network. And well, if you don't have your class, you can just use the loss from the teacher. And this is actually all you do. So I think many of you would know how to implement this very easily. Just add, another token at the end and compute your loss from it. And there were like 2 variants of distillation tried out. One was soft, and I'm usually the soft guy, meaning I like soft solutions, because hard solutions are like, for me, you are losing your information by just deciding beforehand. And so I really rooted for the soft approach. When you are actually if you look at the formula, it's nothing hard. You just have your typical lambda, which weights 2 factors in your loss, and they sum up to 1. So that's why you have 1 minus lambda and the lambda. And then you have your cross entropy loss, which is just a classification loss between the student and the ground truth label y. And the other part of your loss is just KL divergence, which means the computation of how far apart are 2 distributions. And the two distributions is the prediction or the softmax of the student and the softmax of the teacher. So we are trying to mimic the decision of the teacher by the student up to even the mistakes it makes, you know. So if you have softmax, you have distribution over classes. And even though the teacher thinks like, I don't know, this is a bicycle, but it may be a little bit of a motorbike. So we are also trying to teach this to the student. And maybe here, you know, is why this soft approach loses, because you are trying to learn all to teach also like the mistakes to your student, whereas the hard one, you see, it's just the Cal divergence is just replaced with another cross entropy loss, which is between the hard decision of the teacher, YT, so it's the argmax, right, of the softmax of the teacher, and the softmax predictions of your student. So it just tells you like, hey, listen, here is the winning class, the class I think is in image, and don't care about the rest. Just make your own mistakes. And maybe this is even from a father's point of view, is a good way to teach your children. Yes?
Benefit of the art approach is that you don't need the model and to predict the path prediction, but you can run it once on big data and use only the
That's true, but you could also store your softmaxes, right, from the teacher.
it's not your API, then you don't have the softmaxes.
Yeah, I mean, yeah, that's also some kind of like benefit of it, let's say. Yeah. You know, I'm always the guy who's looking more into the meaning of the methodology than the practical properties. That's why I'm in academia, right? So yes, you're right. And then there is some interesting things that are going on in there. So the class and the oh, sorry, Jirka? Yeah, the hard approach is better. Yeah.
We have the approach like the opposite of label smoothing, right? You say this is the only correct answer.
But in label smoothing, you distribute your evenly or randomly or some, you know, so maybe that's the difference, because now the teacher is forcing you to make the same mistake I did. Yeah, sure. But now, you know, now that I think about it, when I talk to students, I usually tell them about my mistakes so they can learn from them. So, but I do not force them to make the same mistakes. Yeah. 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 So yeah, it's like we can have maybe a deep philosophical discussion about this, and maybe we will, right, afterwards. Yeah, it's true. Okay, and so what comes out of this? So class and distillation tokens actually converge to different vectors. So when I come back, for me, when I studied vision transformers without the knowledge about transformers at all, from the NLP approach, I was wondering like, what is this class token? How does it work? So you just so now I'm telling you about the mistakes I made, right? So it's actually randomly initialized, right? And it just learns, and after the training, it just becomes some learned constant. Yeah. So it becomes it's learning, it's turning, it's stretching and everything, and then it stops. Yeah, and it's done forever. And now, as we are doing inference, it's just self attends or attends to the other vectors. It changes, gives you the final, let's say, vector, which is then classified by our multi-layer perceptron. And the distillation token starts from, you know, a different position, and it starts to learn, turn, and everything does, and they end up very differently. There is only you know, cosine similarity of 0.06 between them at the end, which is unexpected, I think, because you can hypothesize about they will end up in the same you know, same position or orientation, because you are giving them the same information, almost the same information, right? But it does not happen. But as they go from these different orientations through the model and they are attending the vectors, they end up in the same orientation. Yeah. So this gives us the idea that they are learning something different. Yeah. Okay. And they also, tried to do like, what if we just, randomly initialize two class tokens and give them the same information, and they end up with a very high cosine similarity. So they end up in the same position at the input. Yeah. So this is something interesting. Yeah. And hard distillation is simpler to implement, let's say, or at least from an engineering point of view, because you already have it prepared, right? And yeah, and it has been shown that this is very good to fine-tuning on higher resolutions also. Okay. And this brings us to Dino or Dino. It's actually aka self-distillation, or sorry, distillation without labels. So the approach, the date approach, which was 1 year before Dino, it had to have some, information about the ground truth. And a lot of self-supervised learning was done, in the meantime. And Dino is like the final solution to this. We are going to take distillation, we are going to take self-supervision and just put it together. And what it means, actually, how is the self-supervision performed in Vision? In Vision, we have this great advantage, I think. I'm trying to sometimes think whether this can be implemented in language also, but I'm not an expert, so I leave that to the experts. But in Vision, you can do geometric transformation of your image, and you are sure that it is the same class. And this is the main point. So I'm thinking whether because I don't know whether some self-supervision is done in NLP. I guess there is the masking learning representation, right? But it's not like I will change the syntax of the input sentence, but keep the semantics and learn it like this. I don't think there's such an approach. And I don't know whether it will be a good approach, but in Vision, it's the one approach you want to have. And it's very logical, because if you look at the object and then you just do this, you are not like, whoo, confused, like what happened? Yeah. Even the dogs, I don't know why dogs do it. Like if you see a dog and it's wondering like what's going on, the dog will go just, and look at this. So that is something, yeah, that probably is also encoded into our vision systems. And so the Dino actually takes advantage of this. They were using also, ResNets, like convolutional neural networks as the backbones, or transformers. And transformers are used predominantly right now. And here in the images, you can see like this model was trained without the labels, so without knowing what's in the image. And these are the attention maps of your class token after the model self-supervisedly learns, And you can see that the maps of the attention are very, very reasonable and logical and intuitive. So they only, show in the places where the objects actually are. And this is not this is not the usual case when you do your supervised training. It's very interesting. I will show you some images later. So and they also found out that the Dino features are actually excellent KNN classifiers, k-nearest neighbor classifier. So you just need then very simple classifiers on top of these features to do your classification. So what they did differently from the self-supervised way, they used multi-crop approach, which is depicted here. So previous approaches of self-supervision just say, let's do some cropping and some transformation of images. We give one to the teacher, one to the student, and we just say it's the same class, and we don't need to know what the class is, right? Because we know it's the same class. But in Dino, they use this multi-crop approach, which actually handles the teacher and student differently. They give to the teacher, they give they call it like global views of the image, which are these two, and they should depict like the general idea about the image, and the student just see these small local crops. So this is like one of the differences that is going on in the self-supervision domain for Dino. Nope. Okay, yeah, we're going. Yeah, that's good. So these global views are passed to the teacher, and all other views, even the global ones, are passed to the students. And then you just compute the cross entropy between the teacher and the student. So that's your loss. So you go through, the outer summation is done, on the global views of the teacher, and the inner summation is just computing the cross entropy here in their paper denoted as H. Between the softmaxes actually of the student and teacher, and you are trying to find the parameters of the student to optimize this problem, and you actually update only the student's parameters by gradient, so only the student is actually learning, which is actually, yeah, it simulates the reality pretty well. Although teachers are also learning from the students, which is the second point, that the teacher's parameters are updated as exponential moving average of the students' weights. So I am telling you something, your brain should be, learning new stuff, and you don't even understand what I'm talking about. And in a few days, maybe the brain will just, after reading some new materials and so on, it'll find its way. Yeah. And I'm just looking at you, and sometimes I see, okay, I think they understand what I'm talking about. Sometimes it's like, okay, there's a miss, they do not understand at all. So I'm also learning from you, how to adapt my teaching. So this is like the analogy to the approach. And so the teacher is actually learning this moving average of weights. Yeah, the tau are the weights of teacher, and they are updated as a weighted average of it's all of teacher's own parameters and the student's parameters. And also there are two interesting things, that the softmax of the student and teacher are sharpened, and the teacher's softmax is also centered. So here is from the paper, there's this pseudo algorithm or pseudocode which you can read. It's actually the whole method in few lines. So it's good to go through it when you learn Dino, but I don't want to go into details. I just describe them. It's just here in the code. And also you have this diagram, and noticeably you can see that the cross line is just like the flow of the gradient will not go through here. Okay, and what are the implications of the teacher's centering? So we don't have to go through these formulas. It's just to explain what the centering means. The centering essentially means that I'm trying to collapse into a uniform decision. So the teacher actually can say, or the centering is forcing the teacher to actually take the position that maybe the truth is not, so easy to tell. Maybe I should consider other aspects. So if you show me a photo of a dog, I should not say like, yeah, that's a dog for sure. I should say, it seems like a dog, but maybe it's, a cow, or maybe a cat if you look at it differently, or if you put it upside down, it looks like a toy. It's like label smoothing, yeah, actually it is, yeah. So this is like done only for the teacher, and also this is actually work well when you have uniformly distributed classes in your dataset. Because if you would have just one class in your dataset and you would do centering, well, one class you should have at least two classes, but one class would be dominant. You would actually you force yourself to make mistake on the dominant class, because you would try to center the decision. So it works, pretty well for even long tail distributions, but ideally you want to have your classes to be uniformly distributed so that the centering makes sense. Yeah, because if you have like random sampling of your classes, yeah, then the uniform distribution of their probability is actually a good guess. Yeah. The ground truth classes that exist outside of the knowledge of the model. So you do not use the class. I'm just telling you that if you want to do centering, it makes the most sense if you provide like uniformly distributed classes to the model. images depicting different stuff, you know? So you have dogs and cats, you want to have like 1,000 dogs and 1,000 cats. If you have 1,000 dogs and 1 cat, the model will actually start to go biased and will tell you about the half of the dogs that it's probably a cat, you know? So you have evenly distributed classes, it then tells you in half cases there's a dog, in half cases a cat, and it's right, yeah? So that is like the extreme of the centering. Of course, you know, practically it's there maybe for the smoothing of the decision and so on. Yeah, but we can find an analogy to it. The teacher should, you know, sometimes question him or herself, right? And the sharpening, yeah, is the opposite. These are my doodles. I was trying to, you know, I was playing around with my new, you know, touchpad. So that's why it looks like a kindergarten drawing. And yeah, so everybody's talking like the sharpening. Sharpening is just divide by some kind of tau. But you have to realize that it's sharpening only if it's less than 1, right? It's greater than 1. It's the opposite of sharpening, which would be, I don't know what would be the proper word, yeah? So take care of this. And in the papers, you won't even, you know, read about this because it's self-evident and everybody thinks that everyone knows about it, yeah? So I was a little bit confused when I was learning about it for the first time. And this is the implication is that your softmaxes become more sharpened. So you actually want to be like double down on your decision, you know? When you are on an exam and your teacher asks you like, are you sure? You should go like, yeah, I'm sure. Although many go like, now that you ask, I'm not that sure. Yeah, so this is what's happening to the teacher and to the student also. And so just the details about the training before we take our first break, I think. I have then the results for Dino and then we'll take the break. So it's so the model, the transformer is learned from or trained from scratch. So they are not using pre-learned weights. This is very important. And you have the same architecture for the student and the teacher. So that's the difference between classical distillation. Classical distillation tells you you have a larger model you are distilling from and a lightweight model you are distilling into. Yeah, so they have some, you know, linear warm-up and cosine scheduler. I think, yeah, the cosine scheduler to me, I like it a lot. A lot of papers use it. And yeah, my thinking about how to interpret why it works is, you know, the cosine schedule, it goes like from small learning rate, it warms up, yeah, and then it again falls down. And we were taught when we were, you know, doing our, you know, deep learning before that you had this large learning rate you begin with, and then you have steps, you know, and you go down, then you had smooth decays of the learning rates and so on. But for the cosine schedule, my interpretation is that when you begin with random weights, you are totally, you know, far away from the optimum, right? And suddenly you start to getting chaotic gradients because you can go to any, you know, any direction in your, I don't know how many million, you know, parametric space. So when you have from the beginning a small learning rate, you are just, you know, calculating your momentum and trying to find like, where's the best direction to go from all this data, from all the epochs. And only after that, when you decide like, hey, it seems the data are, you know, biased towards this direction, I start taking the steps towards that direction. So this is, I think, this is only my, you know, interpretation. This is nothing that would be, I think, already described mathematically. Okay, and so there are some interesting details. You can, you know, read about it. The most interesting fact for me was that when we see the update of the teacher, it actually follows the cosine scheduler, but from 0.996 to 1. So it actually tells you like almost, you know, like almost ignore the student from the beginning, and at the end ignore him totally. Yeah. So that is something I was not expecting. Yeah. And yeah, another thing that was like interesting to me in Dino features is like, you know, you take your transformer, you take your class token, and you do not like produce the softmaxes for the distillation directly from this class token. You have some hat on top of it, and the most interesting part in this is like the dimension of your head. And if you see in this table, this K is the number of neurons in your head, you know, in your that you are computing the softmax from. And they are not playing around. They have like 65,000 dimension. So imagine when you have your ImageNet, you have 1,000 classes, you have 1,000 neurons at the at your classification layer, and here they have 65,000, and it provided the best results, even though they are not you know, as different from the other numbers. But they actually, when you download Dino version 1 and you use it as it is, you will get the 65,536 neurons in the last layer. And we were discussing like, what's up with this number? And doesn't anyone know what the number actually is? Sanjeev, maybe, yeah. Sanjeev would be like, maybe he would know. Sorry?
65K, 64K, right?
Yeah, something like that. If you remember, back then, before Python, we have these things called data types. And this is actually the highest unsigned integer that was implemented. So yeah, so maybe that was the reasoning for them. Yeah, and also they tried some other architectures. They were using one with a bottleneck and normalization, and one just with the MLP. But this is ablation studies. Yeah, you can work this out on the paper, and you can see that they actually that the L2 norm bottleneck was the best one to use for the optimization. And after this, you actually, you know, throw away your head, and you are just using the class token feature. Yeah, and the class token is usually I don't know how many you know dimensions is your transformer. So it's usually 768, I think, in the default transformer. I think the vision transformers use 512 sometimes. I don't know. Yeah.
So it's trained very much like K-means. So when you say like there are 10 classes and just classify, and you don't say what those 10 classes are.
Yeah.
Yeah.
Yeah, and that's why it works actually pretty well. And yeah, there's the evaluations protocol that usually before that in self-supervised systems they use something like linear probing, which meant that you take your features that are learned, and on top of them you train a lightweight linear classifier, and you just compare it. This is the disadvantages of this is that for each task you need to learn a new classifier, right? It's not, you cannot just take it and reuse it in another task. Yes?
So why doesn't it collapse into some strange point, like maybe the student just says is the first class no matter what, and the teacher becomes the student at some point, or the other way around?
Wait, I will just here's your answer. So since you asked, skip 2 frames, I will go back. This is the graph you want to look into. They had to actually balance the influence, of the terms in the loss function, and is actually the sharpening and the centering that is doing the job. And if you set it like not very good, you will collapse. And here in these graphs, because you can actually the cross entropy can be divided into entropy and the divergence between the signals. So then you can draw these nice graphs, and you see that so collapse study. Yeah. So which one's that? When you do only sharpening, you will collapse like into like everything is just one class, let's say. Yeah. And when you do your centering, then you will collapse to random decisions, let's say. So you have to really like weight them, and so that you get your result. And I'm always thinking about this, like if I would do this experiment, I would probably, after several tries, I will just give up, So I don't know, maybe there was like I'm imagining some student who has his deadline for his PhD thesis, and he's like, there's no time for a new idea. Let's just do hyperparametric search. Let's do it. And he was like doing it like, you know, all night and could not sleep. And finally he found his magic numbers or hers. I think this was a guy. So I imagine maybe it's like this, but yeah, this is something that's not clear to me how people are able to, they must really believe in the idea, you know, to pursue it and to find the parameters and to make it work. And here are other interesting graphs when we are on this slide. So the teacher is always better than the student. Although the student, it's very funny because the teacher starts without any knowledge. So he only pretends that I know everything, right? And the student is learning from him, like, yeah, I believe you, totally. And somehow the teacher is always like more clever than the student, even though the teacher is cheating, actually. He's telling you nonsense. You are like reacting to it somehow. He's observing you like, now they think that this something I said was wrong, so I learn from it. Okay. So yeah, this is another strange phenomenon. And they used also different approaches, like how to do the student and how to do it. So if you just if the student is just a copy of the teacher, it does not learn anything. If you take the student as a previous iteration of the teacher, it does not do anything. If you say that the student is the teacher from the previous epoch, it starts to do something. And if you use this momentum stuff they use in the final solution, then you get the best result. Yeah. So this my teacher and yeah, sure.
There's a competition here. It's different. Like there's the other thing. It reminds me of the replay buffer from reinforcement learning when you've got chess games and you've got the set of chess games you've played and you're learning from that, so that the teacher setup represents the previous games you have already played, and the student setup learns from it. There's a similar dynamic there, so I guess it's
I mean, I've never thought about it like this, so but I like it. Yeah.
It was very sensitive because whenever the replay buffer became filled with nonsense, the training would just collapse.
Yeah.
It was very
yeah. Reinforcement learning is something that I do not know a lot about, but yeah, but the GANs, yeah, I know this was like back then Wasserstein GANs were the ones that solved this a little bit and so on, and nowadays, you know, it's done totally different. So let me just go through fast. Here are some results. They are the best. Maybe, you know, compared even to supervised approach. So you can see that we are always behind with Dino, behind the supervised approach, but it's like the best self-supervised method. And yeah, more results, unimportant. Here is something interesting. These are the attention maps of different heads of the class token. Yeah, so each head is drawn in different color. Yeah, so you can see that the heads actually specialize to something. And nowadays, Dino features are used, for example, for depth estimation, pose estimation, and you know all these tasks. And really, I think, and I also spoke with Florian about it yesterday. Like, when should I use masked autoencoders, and when should I use the Dinos? Yeah. So he did not have an answer. He just answered like, yeah, we did some studies at Meta, but it was due to budget, we had to stop because it's not a critical thing to find out, yeah, for them. For us as scientists, it might be interesting to study this. And from my view, Dino usually performs better than masked autoencoders when compared, you know, head to head. But not many studies do this. Usually it's like, you know, two camps. One Dino camp and one masked autoencoder camp, and they are like not that much, you know, comparing directly. But I get the masked autoencoder idea comes from the idea of masked learned representations, and this is totally different approach. No masking here, you know. So this is interesting that the emergent properties are here. And this is the other interesting image you want to see, because the supervised methods, when you compute the attentions, you can see that they like to, you know, look a little bit around the object. like on the environment and so on. This was actually addressed by other papers. I don't know the name, but they are using some register buffers there are actually some additional tokens you give to your transformer just to handle like some unnecessary information so that you get better maps or segmentation maps. So this is interesting because the Dynamo features actually they focus on the object itself. So and it's self-emergent, right? We did not force it to do it. Just found out that this is a good thing to do. And then you have these ablation studies and so on. So this is, if you are interested, we are running out of time, so later. Well, in the self-surprised scenario, you don't care, right? But usually you use 1,000 classes from ImageNet in these experiments. No? Okay, and yeah, there's some feel good images when you report your results. You wanted them to look good. So I'll just leave it hanging here, and with this we can have our break. So see you in what? 15 minutes, 10 minutes, 15. Okay, so 10:45. Too much? No. Ještě nás čeká půlka.
Je to dobrý.
No, Dino?
Aha.
Taky mě to baví. I need my coffee. Yeah, coffee. A vypněte mi ho?
Jak se to vypne?
Tady někdy podržte, než to zasne. Okay, guys, so let's continue. Oh. Okay, so in the next part, I'll talk about sign language. And also, I had one interesting comment during the break, which I want to bring up too, that I said that there is like no new architecture going on. And so I was told, and I reminded myself about the state space models. So which is, you know, a marriage, let's say, of deep learning and control theory and state space representation. Yeah, and these are very interesting papers. The Mamba model is the most current one. So have a look at it. We were discussing like maybe it's the next new step, but yeah, it needs some time, you know, maybe for optimization of the implementation and, you know, bringing up the community. So if you are looking into something new, check it out. Mamba, you know, like the snake. I think Cole Bryant was called also Black Mamba, I think, something like that. So it's easy to remember. And we have in Vision, there is Vision Mamba, and yeah, it of course works quite nice. But for now, I mean, it's mostly in this kind of domain, right? We are able to produce some results that are like good looking. Okay, so sign language. I came here as a team leader of the sign language translation group, and I have to confess, I do not know sign language. And we have one team member, Richard, who actually knows sign language. So Richard, I'm counting on you to bring very valuable information to our team. When I was observing you, when you were signing, I was like going, okay, this will be a problem, you know, because when you look at the sign language in television, there are interpreters who are people who learned sign language as their second language, let's say, mostly, you know, or at least in Czech television. And you know, when I speak to people from the community, like, what do you think about it? I get very, very different opinions. Like someone will say, the guy does not know how to sign. He's totally making up his own stuff. And other one will say like, he's the best guy, and you know, he signs very, very well. And sign language is a natural language, you know, and you have many, many ways of expressing yourself in, you know, speech. So everyone has his accent, like me, like everyone here, and every culture, let's say, is using its own expressions, terms, and you know, even grammar. And even though it's considered to be still, let's say, English, in America, you can find many forms of it. Yeah. And so, of course, someone from East Coast will tell you that the guy from California speaks nonsense and vice versa, right? And the same is in sign language, yeah? Because, but it's maybe even harder because the communities are smaller and more isolated. At least I'm talking mostly about the perspective from Czech Republic. So there is 10 million of Czechs around. So yeah, I did the +1 when I got my citizenship, and there isn't that many sign language users in Czech. It's estimated to be something around 20,000. So the communities are isolated also because it's not like there's one town of deaf people, you know. They are distributed, you know, uniformly throughout the we can say even planet, right? And I am imagining like if I would not be able to, you know, hear, and suddenly someone invents, you know, CDs, compact discs. So how have you learned about like how should we call it, right? It was like published in some, newspapers, people in television talk about it, and it suddenly became like a second nature to us, like it's a CD. Yeah, nobody is calling it compact disc or turny shiny or something like that. Even though kids might, come up with this term. But in sign language, it's harder because they have to come up with the sign on the spot. They do not have like this huge community that would support the idea like how we should call it. And in Czech, for example, one community will sign the CD like by the shape, like it's a round disc. Someone will like spell CD or just C or something like that, like this in ASL. Okay.
I'm showing it to you from my perspective.
Yeah, I have to turn. And now I don't see. Oh, shoot. Yeah. Oh, like D. Yeah. So it's like spelled like a lowercase D. Yeah, right. So yeah. So but I've seen different kinds of interpretation. Like they are using, for example, circle like CD or like this. Like when we had Discman, it was called. Probably you remember. Okay, this someone is with me on this. Yeah, so this is a big problem, right? And then, of course, the guy comes to the television and starts to interpret everything. And of course, someone is like angry with it. Like, what language is he gesturing? Let's say. Yeah. So there are many problems like this, and I think that with the advent of internet and social networks, there might be a way how to, let's say, promote the community to connect it together more. And we are now, having HD 4K, 8K video, so the connectivity issue is not there anymore. And we can support this with some applications of recognition, let's say. And we can even connect then people who are using sign language with people who do not use sign language. Yesterday I was talking with Florian, like he was asking like, well, what do you see like the application for? And we were in a bank as foreigners from European Union. I got my first check in my lifetime. So I did not know what to do with it, right? So I asked, and they sent me like, you have to go to a bank, set up an account, and deposit your check there. And I was like, oh, okay. So I went to the bank, and one of the first questions was like, are you eligible to speak in English? I said, yes. And we did speak in English, and they said, well, if your mother tongue is Czech, we would just call an interpreter, right? And this is the state of the art for sign language users, actually, also. So if you come in Czech Republic, there is a law that everyone can use the language of their preference. Meaning, yeah, there are some, official languages. Only one, I think, in Czech is, maybe it's two. It's Czech and Slovak, probably still. And but the user, a deaf user, cannot be forced to use spoken language. He can choose to use his own sign language, his natural language. And that's why every public place, like police, fire department, or banks or post offices, they have to have access to interpreters. So that is the state of the art. They just take out some laptop or some whatever kind of technology that is capable of transferring videos, and they just make a phone call and they are connected and they can discuss. But of course, the people there, they cannot just go home, and the interpreters, I mean, they cannot go home and they cannot just be like, today I don't feel like working. They have to be like 24/7 almost, on the line. So the institution has to also pay for them for being idle. And it does not happen, when you have like only 20,000 people in the whole republic who are like theoretically who would use such a service, then of course you are like losing a lot of money just to pay people for doing nothing, let's say. And so this was like my let's say pitch to Florian, like why Meta should be interested in this technology, because maybe the institutions will be interested in saving the money. And in scenarios when you are setting up your account, actually there is not much, decisions you can do. And you have a pretty well-defined domain. You are talking about, some kinds of account and time scheduling and money and this. So it's a pretty close vocabulary, right? So I think it's feasible to do it in these well-defined scenarios. And that is something that we, are moving towards even with our project. Even though we are aiming at the general translation of the language, I don't think that it can be, used in a general way yet, because there is simply not enough data and so on. And here I asked ChatGPT, what do you think? What is sign language? And this is the reply. So it's a wall of text, but I will just, compress it to, it's a rich and complex form of communication, right? So many people think that there is only one sign language in the whole world. And majority of people think that. But I don't know how, how people can think it, because it takes maybe a few seconds of like imagining like, okay, how would a guy from Australia communicate with a guy, in China about what is the sign for the, let's say, moon, and how would they teach it? It's the idea of Esperanto, right? Universal language. It was tried and it failed, and it's because it's forced language, right? It's artificial, and people want to use their natural form of expression, which comes with their culture and from their parents and so on. So sign language is the same. You are learning it from your parents or from someone from your community, and you are adapting it accordingly to your surroundings. And people from different cultures can have different opinions about things, right? So that's something I want to remind people of, that it's a natural way of communication, and it's not an artificial way. In our let's say, darker period of existence in Czechoslovakia, when we were under the regime of USSR, there were some, or not some, but only, there were forms of normalization. For example, you cannot be left-handed. Yeah? If you were born left-handed, you were just forced to being right-handed. You could not speak in sign language. You had to learn how to read lips, and you have to learn how to speak, even though you could not hear yourself. And that was, I mean, from the perspective of the Communist Party, it was a great idea. Maybe even from, if you think about it like utopistically, it's maybe a good idea to try to normalize people, because then you have less, ambiguity, less noise. But from the perspective of people who are living creatures with emotions and desires and so on, it's not the greatest idea in the world. And also it failed. And from the history of our country, it's led to the revolution, and in the whole Eastern Europe. I think this was the main idea behind why we want to be free of communism, because we saw that it's forced us to do something that is not natural for us. And I mean, I don't want to get, geopolitical and stuff, but I already did, so whatever. But they might be, cultures that cope with communism quite well, and it might suit them. But it wasn't us, yeah. So, and you who already, I wanted to say had the pleasure, but I don't know whether I should use the word, speaking with me in private, that I would suffer so much under such strict rules. So yeah. So, and for sign language, it was interesting. I mean, I spoke with a scientist who actually developed a clever idea, because, as I said, they forced deaf people to speak, but they could not speak. And if you now, if you are in contact with a deaf person, you know that their language is like, since they cannot correct themselves, it doesn't sound fluent and natural at all. And so they developed actually a system where they recorded what the voice, let's say they were teaching the word matka, which means mother in Czech, and they actually showed the waveform to the person, and then they recorded their voice, and they compared, the ground truth waveform and the waveform produced by the person, the deaf person, and they had this visual feedback. on the language. Yeah. So they were trying actually to draw a waveform by using their voice. It was waveform. Yeah. So it could have been spectrogram maybe, but yeah. Maybe they had both. I don't know the details. Yeah, but yeah, it was, it was 50 something. So I don't know even the technology. It was maybe oscilloscope to show the, to show the results. So yeah, so I'm not sure about the details. I just spoke with the gentleman who developed it in Czechoslovakia for 5 minutes. So and so this was like the idea behind it. And I mean, if you have to do it, it's a good way to go, right? I remember myself when I was at some kind of conference about languages. They had this nice like you had a profile of the person, and it showed you like actually the insides of your tract. And I don't know why, but it really helped me to pronounce, the accent as like better, because I somehow knew internally what should I do with my tongue, what should I do with my, throat, and so on. So yeah, definitely it's a nice idea. I don't know why this is not like more mainstream for when you are learning languages, because yeah, it really helps. Yeah, and so what about the sign language? So we are taught that there is two main components of the language. It's a manual component and non-manual component. That's the general distinction. And the manual component is about like the movement and the stuff you can observe pretty well. So it's like the hand shapes. So as we saw, C D, right? Thanks. Oh, thank, or easier, thumbs up, right? And there is the movement, yeah, whether you wave, you can go like this, yeah, and you can do symmetric movements of both hands and so on. Then the location, where is it performed? So whether I do like this, you can, yeah, you can understand. I remember because when my child was so young, he could not speak. And it was so funny because I woke up and I was in a really bad mood and everything, and I did not want to see anybody. And the child came. It was like 1 year old or 1.5 years old. He looked at me and like, Papa, huh? And he was like referring like my eyebrows like this, and he was like, he could not say like I'm mad, but he showed like this, and I was like, okay, this is what. And my, I was all right, and I was happy afterwards. So he actually corrected my, my emotions or made them better. Yeah. So this is something that is deep inside of us, right? The gestures, and so, but if he would do like this, yeah, so it can be a very, very similar, hand shape, but sorry.
Yeah, like when I was like a baby, my mom usually like babies can't talk well, but when I was like, like all of my siblings and I, like we all like do sign at like the age of like 3 and can communicate with our moms and like dad. So like I think like sign is definitely like different in terms of like how you learn it and like.
Yeah, that is. I've heard about this when in families of hard hearing or deaf people that the children learn it at a very young age. And do you remember? Have you understood the semantics of the stuff, or like was it really easy for you? I mean, how was the level of expression that you could do? Do you think when you compare to speech, do you think it's like very more expressive or?
Let's try something. Brian, can you check if he speaks into this, whether the audio is any better? Yeah, just talk.
Oh, okay. Yeah. So like, for example, when I do like when I was like talking, like sometimes like I can't express something in speech that I can in like sign. Like, so if I say like hungry like this, like sometimes I'll be like I'm really hungry.
Yeah, you showed it.
Yeah, like compared, like I'm like a little bit hungry, so you can kind of show like the emotion of that.
Yeah.
I don't know why I'm signing right now, but yeah, you can kind of show the emotion of that through like your expressions, like I'm sad, or like I'm sad. You know what I mean?
More
Like, it's, like,
sadder, yeah,
it
yeah.
really shows the emotion, and like sign language. Like I feel like I can't express like there's sometimes like sure you could use words like that you might like have like I don't know, like an example, like for very angry or something like that. But like, yeah, it's like in sign language, it's like easier to express yourself, especially in like your feelings and emotions and like the way that like I know it's just facial expressions there.
Yeah.
Like so like there's a lot of sarcasm in sign language too.
Okay.
And then so like I could be like someone could be like asking me like, oh, do you know Richard? And like I'm Richard, obviously, and I'm like, yes. And like, it's like very sarcastic.
Hmm.
Uh,
Okay. Thank you for the addition. This is actually the expertise we will need in our team. So thank you for that, for the demo. And yeah, so it comes naturally, right? And yeah, and there's the last part is palm orientation. So yeah, you can do like this or like this, and it can mean different things, right? And the other part, so and manual components, when I was doing my PhD, was like everything I was concerned about because I was like into vision. So how to detect the body parts, how to detect the movement, the shapes. These are the things that are pretty well described in vision, right? But the non-manual component is actually the expression, as you understood, like whether I'm sarcastic, whether I'm serious, whether I'm angry, you express by face. And so it's like different modality of the speech. But it, from my understanding, it's maybe more important than the signs themselves. Yeah. So this was neglected a lot because it was hard for the science.
Sorry.
Of course. No, please go.
About signing, but it's like a very it's very important to focus on the whole body.
Yeah.
It's like when sorry.
No, just hold on.
Just keep it, Richard.
Just hold on to it. By the way, keep it and just pass it to.
Okay. Okay, but like for example, like if I'm saying like there's like different meanings for like different like ways to say stuff. So like for example, if you want to say voice like this, you use like I don't know what this is called actually. I forgot what it's called. Yeah. You're tricky, yeah. Or like if you want to do like heart, you kind of like make a heart on like your actual heart. So yeah, it's like definitely important to like use like location with that kind of things. And facial expressions too and body language, yeah.
Yeah. So and they are very nuanced, and our brains are fine-tuned on the expressions and on the identity, of people. When our brains, went through evolution on this because it's very important. Empathy is very important for communities, right? So that you understand how the other person feels, and you just make a micro movement, and suddenly, everything changes. The expression of the person and what he's or she's trying to express suddenly changes. Yeah, when I go like this, I'm like, really seriously, we should do something. Or when I go, really seriously, it's the same words, but it's totally different meaning, right? So this is actually a big challenge in vision. Because computers do not understand these distinctions, and it has been shown, or machines generally, in generative models, that they have no problems generating 6 fingers because it's just few pixels in the whole image. I've generated such a good face, such a good arm, and everything. One more finger, what can it do, right? And there was also this commercial on in our, I don't know, maybe it's international, on the toothpaste. I probably will not say which one. Yeah, I'm not paid, so I will not say it. And it was like people were, having a little dense, little dark things in their teeth or some kind of stuff. And you looked at it and okay. And after that, it was probably you did not mention that the person has 3 arms in the first image. And you just go back and, whoa, really? And there were like totally visible 3 arms, but you just missed it because you are focusing. It was like the commercial was trying to even make you think about your teeth more, about the rest. But it's true, like when you are talking to a person and you see this one annoying, bit of the food in their mouth, you're like, oh, should I tell him? Should I not tell him? And then you are feeling uncomfortable, right? And the same is when you have like dirt on your small little dirt here, then you're like, oh, I don't want to look at him. It's like it hits you so much. Yeah, and it's connected with this empathy, I think. And maybe when people were in the communities before, they were, there was a disease, so that you can identify it as quickly as possible, right? So I think it has evolutionary advantage also. But from the position of vision, it's just, you know, few pixels. And if you do not give the machine the meaning, you know, machine, we do not have sentient machines yet, yeah. But for the machine, it might not be important, you know, like it's just few pixels. Why does he care, you know? But it maybe it will, you know, you have phone. When you open your phone and your eyes, you know, go either for time. You want to see what time is it, or what's your battery life, right? So maybe machines will have something like this, like there will be robots moving, and suddenly it goes like a little bit clink, and you in his maintenance, and they will maybe focus on totally different parts, right? The machines. So this is something we need to actually force the machine to see, and it's hard to do. And this active, you know, field of the vision and the emotion recognition and so on. Yeah.
Is that a problem just of generation, or is it a problem of recognition as well?
It's both, and recognition as well. And maybe I would say maybe recognition even more, because it's really in the image only few pixels change, and if the change happens somewhere, you know, on the background or on my chest, the same number of pixels change their light, their brightness. It's totally different if it happens, you know, on my forehead or on in my mouth, you know. And
What kind of techniques of like what kind of recognition we're talking about? I'm just working a lot with eye tracker, and one of our studies focuses specifically on details of the facial expression. And I'm very curious what you are using, or like why is it not allowing to focus on those details?
Yeah, so we are using generally, you know, like the vision models I demonstrated before. So convolutional neural networks, transformers, pose estimation. I will have a little bit of slides about that. So, and these techniques are usually, you know, like semantic based, like they are looking at the whole picture, and they do not focus that much on the details. And even though if they do focus on details, like dino features are more focused on to individual patches, they do not yet understand that the position on your body is important, because it has not been, you know, you need to, for example, design a new loss function for this, like really penalize it, like you missed that the eye was doing like this because it was like a few pixels. So you have to like you know, if you do like many motion here, it does not mean anything, but if I do small motion with my eye, it's a switch, and a person sees it instantly and knows that this is something important.
I know that it's not realistic in some real tasks because it's crazy expensive, but do you think that start was using of the technology that allow more precisely identify emotions? Like you can use eye trackers with a very high resolutions, or like get them really close to the face, and then you can notice like even the smallest facial expressions. Can you start training the model with it and start adding more noise to it? So it's gradually decreasing in quality and gradually increasing in noise. But then you see kind of this time series of, okay, it started with a very high quality. Like, would it allow machine even on the high noise to better recognize those small changes?
I think that's possible. There's an idea worth pursuing for sure. But for me, I don't, personal view on this is that I don't think technology is the problem. The problem is the design of the system. Because as I said, our brain is hardwired differently. We are not general, you know, recognizers of the reality. We are very, very biased towards things that we care about, you know. So and it's due to the, let's say, evolution of, you know, biological and social and everything. So we need, for the machine, we need to force the machine to do this by, for me, it's like by designing a loss function that would, you know, penalize these errors like with a really big penalty or something like that. Yeah. So
maybe I would think it's more due to the data, because like when you pre-train, let's say Dino, you pre-train it on images of scene. Like when I'm working in the world, I'm looking at objects in the world because I'm moving. I don't want to hit anything. But when I'm sitting here in the lecture, I'm looking at your face. And when someone asks a question, I'm looking at their face. I'm constantly looking at faces. So like these 3 hours, I've been completely ignoring the objects in front of me. I was just looking at the faces. So maybe it's just a matter of the data the model is pre-trained on.
Sure. But what does it mean you look at the face? Because I see a wide array of image, but I focus on your face.
Yeah,
So that is something that the computer has different, because it does not know that the pixel up there is less important than the pixel in front of him, unless we, somehow some inductive biases to be inputted into the
yes.
system.
So like have a face detector and increase the weight of the error on the face, something
Of
like
course, there's one approach. I mean, you can do this, but I think the main idea is that it's not solved in mainstream computer vision. Let's say the mainstream is focused on big things, yeah, and the things that bring the most money the fastest usually.
Well, there's also a difference in the way camera sees world and eyes see world, because the eyes see a little patch of what I'm looking at, whereas the camera sees the whole thing uniformly, importantly, right?
Yeah, and the vision, the human vision, because animals have it differently, right?
Right.
But the human vision, you have a center region where you really see so many details, and the rest is focused on motion. So if something moves here, I go like and start focusing on it with my central focal
just an idea,
region.
take like edit a set of humans in scenes, detect all the faces and blur everything that's not a face, and then pre-train the model, because then it has to focus on the face or the
something
sound.
like that.
Maybe.
I mean, something like that. But for the sign language and emotion recognition, I think we need to go to into even more detail. So maybe super resolution or something like that. Like, okay, take the face image, do super resolution of it, collect all the wrinkles, that are there. Yeah, something like that. Yeah. Well, it was oppositely meant, right? You say, let's go from the super resolution and like distill maybe information into the lower resolution. Yeah, it can work. It can work. Something like this. Yeah. Okay, so good discussion, actually. Richard? Okay, sorry. I was hoping that whether I do have enough slides, so thanks for saving my lecture. Now I have, I think, the opposite problem. I will not. I have the last slides on image generation, and I want to get to that because I think it's interesting. So let me go to the next slide. This is a slide about sign language translation. It's from a German dataset, Phoenix, about the German weather. It's very much used because it has something that it's hard to do. It has annotations, of the different glosses. And a gloss is something as a direct translation of a sign, let's say. So you can see that, okay, you can probably read it in German, dazu kommen mild darum ab Freitag Schnee nicht mehr. So it's crazy, in English, to come mild, therefore from Friday, snow no more. So it's totally, differently like arranged. But you can get, maybe the idea, the general idea. Yeah, as milder air flows in, snow is no longer a concern on Friday. Yeah. The German one is a little bit harder. How many people actually speak German? Show of hands. Okay, few. Yeah. The Eastern European guys. Okay, well done. Yeah. Okay, so this is what is interesting about the Phoenix dataset, that you can actually do sign language recognition. So you can take a part of a video and classify it as a word, as a gloss. Dazu is the gloss, or to, right? So it's like in NLP something like a lemma or something like that. It's a basic form of the word, yeah. And so this is recognition, just classifying the glosses. And there is not a lot of, there is a lot of data sets for isolated sign language recognition, where you only perform one sign and you just classify the whole clip into one class out of many. This is continuous recognition. So you have to find the segments where the sign starts and ends, but you have a one-to-one mapping, let's say. And then there is translation. And the translation is actually directly from sign language into its spoken form counterpart. Yeah. So that is what we are doing actually in this workshop. Because this is, this is old school. This is already like pretty well on the last data set was Turkish data set out cell, I think, and there was 220 signs, I think. Karahan, you remember? Sorry? Yeah. So around hundreds of classes, and winner had like 98% recognition rate, something like that on test set. Yeah. So it's quite well understood, and now we are moving to the continuous, and with the transformers we can do even end-to-end translation, right? So this is what we are going to do in this workshop, what we are trying to do. Which actually needs a lot of expertise from different fields, and I have like a really good team. So this is very good because everybody can add its own his or her own perspective on it. Mostly, I think we are missing NLP guys. So if someone from but I mean we have some. I mean we have you, Dominic. But for vision is like killing it. We have like 10 people from vision. So if anybody from the other team can somehow, sometime come and visit us and just critique our work, but not that much, then yeah, it will be very helpful. And let's get to the pose. So here's an example what the pose is, because it can mean different things to different people. So here we show this is like a pose of the face, let's say. So it's like the shape of lips, eyes, and position of nose. We have to distinguish between shape and pose, right? When we have even the hand, many people say hand shape, but we found out that it's actually we have to distinguish between hand shape and hand pose, but most people do not do this, right?
I was curious to know if for the data set that you're using, do you already have alignments like between the frames and the transcription or whatever? Or do you use like things like CTC loss, like to find the alignment by yourself? Like, how do you do that in practice?
Yeah, so in practice, there is a few datasets like the Phoenix dataset, which is around, I don't know, this is 30 hours, 20 hours, something like that, which has this alignment to the glosses. But then you have only weakly aligned data. So we have actually, what we are using for pre-training is YouTube ASL, which has like only captions, in the YouTube videos. So it's weakly aligned and there will be mistakes and so on. And then we want to fine tune on how to sign, which is like a more controlled data set, which is always a clip and a translation. So it's also not aligned, but we do not use CTC loss. We simply use transformers. So we can just predict like the next token and do cross entropy loss as is in standard transformer approach for translation.
CTC loss as an auxiliary loss function to help the transformer to learn the alignment between frames.
Well, we are not using anything yet. We are going to try most things, but the baseline approach would be just predict the next token. Yeah, and we hope that the transformer will learn it in the cross attention module, right? So yeah. Yeah, that was the standard approach from the 2017 paper. Attention is all you need. You just classify using cross entropy loss, right? Yeah, because you actually lose this problem which you have with speech in language, right? But for us, it's like it's hybrid. So maybe we will have to use the CTC, but we'll see how it goes. Okay, so as I was speaking about the difference between pose and shape. So the shape is actually like really the shape of like how long are my fingers, how thick they are, and so on and so on. And the pose is what I do with it. Yeah, and many papers confuse this, or use just the hand shape for it. But if you want to be like really strict as a reviewer, you should say like, oh, but this is pose, this is not shape. And so it's the same with the face, because
like this is a shape and this is the same shape, but it's a different pose.
yeah, your hand is always the same shape, no matter what. So let's say that shape differentiates between people, yeah, and the pose differentiates between the meaning of the performed pose, yeah, something like that. Yeah. So with the faces, of course, and as I said, we are very sensitive to faces. We have a specialized like center in the brain that is used to recognize faces, and you know that there is a disease actually, that when people have damage in this part of the brain, they lose the ability to distinguish between people, which must be terrible and also interesting, but mostly terrible. And yeah, and the pose would be like how much my mouth is open. And when I say oh, and you say oh, then the pixels will be different, but the meaning will be the same, right? So the shape is different, the pose is the same. Then you have this body pose. Usually, when you are detecting actually the joints on your body. And then you have the hand pose. And it is maybe something that is not clear straight away. You have more joints on your hand than on the rest of your body. Yeah. So actually doing hand pose estimation, which is like, let's say my most recent domain, can be said it's harder than doing the whole pose, all the body pose estimation. Also, you know, in the hand pose estimation, you have much more occlusion going on. You have like you have self-similarity, meaning the fingers are really similar one to each other. Whereas if you mistake your hand for your, foot, then then your system is pretty not that good. It's pretty much not that good, right? Okay. So, and this is like the pose definition for the face. So this is just, a flattened, let's say, mesh 3D model of the face. And I'm highlighting here like some selected vertices of the mesh model that are important to define the pose. And so the mouth and the eyes and the brows are the most important, yeah? And the brows are very problematic because usually the models, they model it with few vertices in the mesh, and they just do not care like whether it's like this, like the subtle differences are not that important. But as we've explained, they are very much in the real world. Yeah.
Yeah, just to add on to that, it's like, sorry, I was talking about like eyebrow movement. Like if I'm like really with my like eyebrows up versus like really like
Yeah.
it's like obviously.
Yeah, and there is a study or more studies that are correlating the why questions with raising of the eyebrows. Yeah, which we do also in normal communication, right? Okay. So and the nose, we have the nose just for the reference because you do not use your nose that much for expressing emotions, but it's good to know as a stable center point where you could use it to express the other vertices relatively too. Yeah.
So even though it's not a clear expression, how much we push upper and lower teeth against each other. I don't know how to appropriately say it. Crank your teeth, or
Yeah.
like this tells a lot about emotions that are trying to be hidden. Can you actually tell the difference when like my jaw is relaxed and cranking my teeth?
No, yeah. So just to be more detailed, this is the posal like description of this stuff, and you of course for these nuances you need the texture. So that's why we want to use the dino features to describe the face and the hands, but also the poses to give it some kind of reference. Yeah. So we will combine this. So the pose is maybe the pose like this will distinguish between the sarcasm and between the why question and between seriousness or something like that, or but then we will need definitely the textural features to describe these details. Yeah. Okay. So, and this is the pose definition of the body. Yeah, so this is like, let's say, the most recent graph model of the body that we are using. So there is 33 actually points that are being estimated when we are doing our benchmarks, and yeah. So here I just wanted to show you like what we are doing. So you can see the hand is like modeled by four vertices, and then you have the 21 locations for your hand. So even though I said that there are more joints in hand than in the whole body, for the estimation we use more than just the joints, right? So then the body wins a little bit. Yeah, and this is the usual model which is used for the nowadays for the estimation. It had changed. Before there were like less or more populated poses. Yeah, so maybe the most interesting part, maybe that the thumb is like the special one, yeah, the finger that has like more flexibility and more joints and everything with some bit of a muscle, right? I was thought here that because some guys here are doing the climbing on a wall and that you do not apparently have any muscles in your fingers. So if you lift weights, nothing much will change, but there is some kind of change in the inner structure, so you can get stronger, yeah, but not by doing, like weightlifting, but more like to holding onto something and, hanging from a tree or whatever, or from a rock. Okay, so, and this is our paper from, what was it, 2020, I think, with one of my younger students. This is a cool story because I was approached by a 16-year-old student, like, hey, I'm doing sign language, can I come show you what I do? I said, yeah, okay, come. He came and he showed me, and I was like, I was a little bit afraid, that he will show me a research that is just 2 levels better than mine. That fortunately did not happen. So he showed me something and I said, okay, my boy, so this is how we do it, yeah? And we did and we did because he was really like, he was just 16, but he already knew how to, fine-tune deep learning stuff. He was doing NLP and so on. So it is Matyáš Boháček. Now he's at Stanford, actually. He was like approved without doing any tests, and and MIT wanted him and so on. So this was, good for him, right? And just a funny story with this, because he came one day after he ended his high school, and he came like this, like, oh, Mr. Rus, I have to tell you something. And I was like, what do you want to tell? I probably will not go to university to Pilsen. And I was like, you wanted to go to Pilsen? Come on, go to America. Okay, I'm going to Stanford. Yeah, good for you. So yeah. So he's now there, and maybe he will visit us. So hopefully, because his schedule is actually pretty tight for his age. Yeah, he's in a first year he ended just the first year of university, and he gives like 2 interviews per week. So crazy. So this is very simple stuff we did, and it was accepted to WACV. And it's just a transformer architecture for recognition. And there is just one interesting thing, because normally when you do recognition, you just use this encoder and you have your class token. And we just tried, what if we just do decoder with one decoding query, which is nonsense actually, right? And it worked so much better. So we just, did some ablation studies, and I don't have actually a conclusion on this. So, but it's something that might be worth trying out, if you are doing our classification, whether this helps you or not. For the sign language, it helps us tremendously. And there is just some, clever way of how to interpret the pose and the advantage. So this is pose-based recognition. Back then, it was state-of-the-art in a pose-based recognition. But of course, we were much, much worse than appearance-based recognition when you have the pixels, right? Because the pixels bring more information, as we have discussed before. But when you have the pose, you can do really, really cool and cheap augmentations. Yeah, so you can have much more data, and also you can do normalizations. So there is something which is, in sign language linguistics called signing space, which is space something like around this, which is the main focus of your signing, and we just normalized to this space, and it brought really like much better results when you do this. So there are some interesting stuff. And then we did some pre-training on this already. So here, of course, it's straightforward to do masking. Yeah. So you just take your pose and then you mask a few of them and you try to reconstruct them, and you have just the MSE loss, and then you can take the pre-trained encoder, put it into your classification module as is, and fine-tune on a classification task. And as Florian mentioned yesterday, it helps you to learn much faster. You learn a little bit better even, but yeah, you learn much faster. So this is post pre-training that we did for the workshop, and we will add new data and fine-tune it or pre-train it a little bit more. This is the pose normalization, how it looks like. Yeah, so this is the signing space, the red box, and you can see the results from the pose estimation. The models for this we use media pipe, and you can see that it also estimates out of boundaries poses or locations for the feet. So this is something that the model just guesses. Like I've seen many poses, so the feet should be here, but I think the model thinks the person is like standing, yeah, so it's not that good. But we are not actually in sign language, and Richard, please correct me if I'm wrong, but we are usually not interested in feet at all. Do you use feet for signing sometime?
No.
Maybe just showing like my heel hurts or something. Yeah. Or how do you sign kick? Like kick a ball. Yeah. So you do not go like. Yeah. Okay. So yeah. And you can see the normalized coordinates there. So we go from -1 to 1 and so on. Yeah. And this is for the face. So we actually, when you use media pipe, which you will play around in the lab works a little bit, just for the hands, you can get 3D coordinates. But yeah, the mesh actually, the face is very, when you take the 3D coordinates of your vertices, you find out that they are very correlated, so you can just get rid of these because you have around 147, I think, vertices on your face, and you can go down to like 20 dimensions without losing any information. And here there are, so we also normalize the positions, and there are the selected vertices that we want to use in our baseline experiments. Yeah, this is mask autoencoder, so Florian was talking about it. But I just want to highlight one thing in this, which is different from standard masking in NLP, let's say, which uses only the encoder architecture, right? But here you do something different. You take to the encoder only the patches that were not masked, and you learn the weights of the encoder, and you only add the mask tokens into your decoder. So that is something different, I would say, something worth mentioning. So you have this encoder decoder actually architecture, and here is some Florian hasn't showed it that much, but these are the results from the paper. So here we have the linear probing, let's say, approach. So you are not measuring, that was important to say, you are not measuring the reconstruction error, but you are measuring the, performance on some downstream task. And you can see the curve is really like at 75%, they get the best results. So usually default parameter for masking is 75%, which is something like this, which seems horrible to be able to feel, but the model is doing quite well, even on the cheetah, on the time clock. So you can see that it cannot reconstruct the numbers properly, but at least because it has partial information about the arms of the clock. It's called arms, I hope. Hands. Okay. So we call it like ruchichki, which means small hands, like tiny hands. Okay. So and you can see that this works pretty well. Here with the bear, yeah, it's blurred and the second bear disappeared. why should he know that there's a second bear when it's totally missing, right? So this is actually good. Yeah, and there are some other stuff you can notice that the details on the, let's say on the espresso, you lose the shape of the pretty flower and so on. And also you can do random crop or random masking, or you can do block masking or grid masking, yeah? And the best one is random. And at least in vision, it has been demonstrated many times that randomness actually is the best way to go. And I like to talk about there's a method for augmenting images. It was called, how it was called? Auto-aug. And they were like really doing a deep study about, it was on Google, I think, like how should we apply augmentations so that we get the best result? And they developed a really nice algorithm. They optimized and they did, and suddenly half a year later or 3 months later on arXiv, there's a new paper called RandAug, which was like, we actually tried to do everything randomly and we got better results. So that is like an ongoing theme in vision. I don't know whether in other domains it's also the same, but the randomness seems, and maybe we are talking about it with Florian one-on-one, maybe it has to do something with the biases, right? Because when you do it randomly, you are like the most unbiased as you can be, right? So yeah, and the model can take advantage from this. And this is our results on the how to sign dataset. So we just, trained it for several epochs, or we took the pre-trained model. And I think maybe Jakub is not here, so I don't know. Jakub is the guy who did the experiments. Maybe this is just the out-of-the-shelf pre-trained model. I'm not sure. But you can see it works pretty well. When we look at the hands, so what is going on? Just so you know. So here we are reconstructing all the patches, and here we are reconstructing only the masked ones. Yeah, so that's why here it looks better, because we just take the patch that was not masked. And what we've observed is that when you are missing the hands, let's say in this, image, oh, there's one hand, but you can see that in the reconstruction, the model does not know what to do with it, so he just put some random blurred hand here. But when the model has information about the hand, about the other hand, let's say, it can reconstruct it pretty well. And this actually, again, this led me to the idea that should we do some kind of like informed masking? Like, should we just mask one hand? But then, you speak for 20 minutes with Florian and you second guess yourself because randomness has been shown to work very well. So that's something that, we want to try out. And again, always when you look at these pictures, it's nice to observe your reconstruction, but you have to think about your downstream task. Will it help the downstream task? So even though if the model is not able to perfectly reconstruct the shape, will it, however, learn a good representation? That's the main question. And our thinking is that we want to use, dyno features for multi-Q representation, meaning that we will crop hands, crop the face. I will talk a little bit more about it on Monday. And but then you lose the general position of your hands and so on. Richard, yeah.
Blurring the hand. Because in that case, like, you would still have like the position of the hand and like some of the figure.
Yeah, I mean, but this is not in the spirit of this method, This is really masked, learned representations. So, but I think maybe it's like it could be like blurred learned representation or something like that. Yeah, so you can
Really quickly, I'm just listening to it and I'm absolutely fascinated because I see so many applications of it and I'm absolutely excited. Do you know because you can use a lot of those methods, for example, on security cameras to predict behaviors that can, I don't know, indicate aggression. Like a person walks into a bank and you can use a lot of, I think, those insights to predict if the person has certain, I don't know, intentions.
Mm-hmm.
Do you know if there are any studies that use similar methodologies for the purposes of like recognitions of emotions or recognitions of intent? Anything like that?
I'm sorry, I have to disappoint you. I don't know about this, but I like your way of thinking, and yeah, because it's totally not my domain. So I got a little bit excited as you were telling you are getting excited. I'm also now excited about this because some guys in our lab are doing actually this monitoring and this behavior analysis and so on. For example, we have a project which has not yet started, but with the public transportation, they are monitoring, what's going on in the buses, and they want to predict aggressive behavior and so on. So I think that it might be worth looking into. Sure. Yeah, okay. So we are running a little bit out of time. Oh, we have 14 minutes. That might be enough. Okay, and just to conclude, you've seen this before. I mostly gave this slide here so that when the slides are shared, you have your, links to some Llama spaces. So I've added the Llama 3 blog, and the blog has the link to the demo. You can try it out on Hugging Face Space. Yeah, so we want to use the Llama to do our decoding of the language, and we want to use the Lava paradigm. So Florian talked about it, so it's pretty easy because you just have your vision encoder. So we will have our Dino multi-Q, our masked autoencoder, and our pose models, and then we will have a projection, which is usually modeled as just one single linear layer, and then we just create these sign language prompts, and then some language instruction. For example, translate the sentence to English or something like that. And we can have also we are now talking a lot about RAGs. What is it? Retrieval augmented generation. Yeah. That we can have some kind of domains, and we can help actually the model to establish some kind of basis, like, hey, now I am in a pharmacy, so probably I should sell drugs. For the European guys, drugs meaning like pills, yeah, not like drugs. Yeah, so and Rex can help because and this is some idea which we already developed with Kevin and then discussed with other people, which is interesting because my initial thought was like, we are going to project the vision features and then do the similarity matching to the dataset. But what if we actually, do the similarity measure on the visual features, and then take the texts that are connected, so to the visual features, like you have a whole video, so we will just match the closest videos to the query, and just take the associated text to the context. That might be interesting, and I've not yet seen it, so it might be even something novel. Don't steal it. Okay, and that's it for this part, and we have like 10 minutes. So let's go quickly through Stable Diffusion, right? Okay. So yeah, bonus material. It was like if we have 1 hour, I can talk for 1 hour. If we have 10 minutes, I will talk for 10 minutes. So again, you have this. You have the link to the paper. I try to put a lot of links. And so the paper is called High Resolution Image Synthesis with Latent Diffusion Model. So, okay, aka Stable Diffusion. So you probably heard about this. Is one of the models. You have several of them. There are the famous ones like Midjourney, and what is the one from the Google? I forgot. Oh my God, the DALI, sorry, and so on. So there is a lot of things going on, and a lot of these models actually use Stable Diffusion. So let me go through it. So this is probably well known by some people. Some people hopefully see it for the first time. And this is the process of diffusion. So it's actually also a physical property of the, let's say, universe, that if you put a tea bag into your hot water, it will diffuse. right? So it'll actually create a uniform distribution of molecules, and this is something that's happening here. So this process, when we go from this side, from x0, you have an image of a face, and you start adding noise to it. And you add noise, and at the end you have something that is quite uniformly distributed or randomly distributed noise. This is the diffusion process. And what you are trying to teach the network is to do the reverse of this process. So take your T and just put it back into your bag. And so we are actually predicting like what was the noise that was added from that step to this step. And you have like T, like capital T steps of the diffusion process. So you have to do like capital T steps of reconstruction. And the details are of the training are, many. Some is that you are not, for example, trying to reconstruct always the whole process, but you start from some other point and you add something like a positional encoding to the model, telling him like you are starting from the third step of the diffusion and so on. So, but this is just the general idea. And the diffusion process is really computationally expensive, and the inverse also. So people from Munich thought about this, and they were like, we should use something different. What if, because here is the graph, like about semantic and perceptual compression, which is happening usually in the generative models. First, the model starts to, compress the semantic information, like I'm looking at a face or whatever, and it does not bother with the details. And later in the training, you have this perceptual compression when you actually start to learn the details, like what kind of face is it, right? Is it a male? Is it old, young? Does he wear sunglasses and so on? And the process of the stable diffusion is actually because this is a costly and non-stable actually process, and you can get confused because the devil's in the detail, right? So you are trying to reconstruct each pixel perfectly, so you lose the semantic value, and you start to focus on the perceptual value. So there must be a better way to do it, and they came up. What if we actually do the same thing, but in the feature space of the image? So let's forget about the pixels. Let's just compress semantically the image into some features and do the diffusion process on these features. And it has been demonstrated that it works much better. You can actually suddenly use just one GPU to train your diffusion models and to train your generative models. So common people with just a laptop can now train their own generative model. And so the idea here is that you take your image, you encode it by some neural network, some pre-trained visual model, which squishes, the model into a lower dimension, and also it takes out the details and leaves the semantics mostly. Yeah, so you pre-train this on let's say on some reconstruction task. Yeah, I will show on the next slide. And then you get your latent representation, and you do the diffusion process. And only after that, you start to do the inverse of the diffusion process. And in stable diffusion, they are using UNet. Hopefully, you know about it at least a little bit. It's a standard, thing that that is used for a lot of tasks, and is now, even though it was actually discovered in medicine when they were analyzing, I think, tumors or something like that. They created this, so it was a little bit from out of domain of mainstream computer vision. But it's in the heart of this stable diffusion method. And so you start to diffuse using the UNet. So you go into some kind of even more latent representation of the latent representation, and then you upscale it back to its latent form, and you do this, like you get the T-1, you do this for T steps, and you are trying to reconstruct the latent representation, and then use a decoder, which is an inverse of the encoder, to create your image. And so some of the details are that this is actually the original encoder decoder that they used in the original Stable Diffusion, which is taming transformers for high resolution image synthesis, aka VQ GANs, vector quantized GANs. What is it? A is adversarial, N is network, and G is generative. Yeah. So here actually you have the encoder. So the method is used for learning the latent representations, and the task is reconstruction. So you get an image to the encoder, you squish it to your latent space, and then you use the generator to again bring it to the image domain, and you use a discriminator in the training pipeline to just tell you how well did you do on your reconstruction. And this quantized version actually, because you maybe know if you studied this, that GANs and variational autoencoders and this stuff usually produce either a blurred image or like non very good looking images according to the connectivity of patches and so on. So this work is, the upper part is the interesting one. I'm not going to talk about it. If you are interested, just read the paper. But the general idea is that we learn a code book of visual representations that seem really, really good, and we will use only them to interpret our latent representation. Yeah, so we are going from some, let's say, continuous latent space to some code book or discrete representation, right? And so this is the encoder of the Stable Diffusion process. So this is, they just take it as it is and put it here. And of course, this is then the decoder. Yeah, and they put it also in the Stable Diffusion at here. So this is like the decoder. Okay, so these are what this is. Just the loss. So really, you are just doing mean square error of the reconstruction of your diffusion step. So we are estimating like how the noise that I should subtract from the noise I have to get the noise from the diffusion process from the step ahead. Yeah, so it's a little bit. We are always discussing why are they estimating the noise. Why aren't they estimating the result after the subtraction of the noise? And well, I think that people from the domain of diffusion processes would have the answer, but we don't know. So we just settled and take it like, yeah, it's okay. We can work with this. And then the most important part, of course, is the conditioning. So because it's fine to encode the image and decode it and have the same image. Yeah, cool. You have your paper. Well done. And now you want people to use it, right? So you have to add conditioning. And that's the part in this image, conditioning. So the cool part of Stable Diffusion was that there is not one conditioning. You can have any conditioning you think about. And we actually did some custom conditionings on this. And generally what they are telling, you need some model that will transform your conditioning into some vectoral representation. So for example, for texts, it can be clip features, which you played with yesterday, right? So you take the text, you put it into your clip text encoder, you get your representation, and you start to add it to your diffusion process. So UNet is just a convolutional neural network. Here we have convolutions, and here we have deconvolutions. The one who just want to kill me is transposed convolution. Okay, so it's the same, even though it's not the same. There's a huge debate about it, but whatever. Deconvolution sounds cooler, so it's deconvolution. And after each block of convolutions, you have this attention module from transformer, and you actually take the the query from the image and key value from the conditioning, and you compute the attention. And this modifies the diffusion step you make. And that's why you are able to condition the diffusion process in such a way that you want it to obey your conditioning. So inject your condition here via, let's say, maybe cross-attention mechanism, right? And so this is the way you do it, and you of course learn the projections into your key value and query space end to end as you go. And now for some results. Yeah. So of course, now it's no problem, but back then it was funny when the models were trying to reconstruct texts, you know, latent diffusion. It's something from out of a meme, I think. Yeah. So they did a little bit better on this. Yeah, and there is a lot of stuff, but don't get confused. This is just the good feel image. When you use it, it will not produce such nice results. We were trying to use it, for example, on traffic signs to generate, you know, a traffic sign that says like Praha or Prague, and yeah, it did not know how to do it properly. But we observed that it actually was trying to generate English texts, meaning it's somehow, you know, biased towards the data set. So it's not fair, and we as Czechs are really disappointed. Yeah. So no, we don't care actually, and we so this is something that is in the model, and here are different types of conditioning that you can use. So because you are used to, you know, condition your models by text, right? Here is the prompt, generate the image, but maybe this is new for someone else. You can do different types of conditioning. For example, here you condition it by bounding boxes and classes of the bounding boxes. And it tries to generate, you know, the image from this kind of conditioning. And you can have really different kinds of conditioning. You can have semantic maps for your conditioning. So you give it a semantic map, and you say this should be a sky, this should be water, and so on, and it can generate such an image. It is also used in super resolution. So you can condition it by a low resolution image and upscale it to a super resolution kind of image. You can see this is actually the latent approach which they use, and they are nice to us because they show us that it fails sometimes. So here you can see there is some strangeness going on, whether when you do not use the latent representation, it's more it looks better. Yeah, it's logic. Like the semantics are there. So yeah, so we lose a little bit, you know, when we compress it into the semantic space before we do the diffusion model. So we lose something also. Okay, and then the last example is how do you say it? Not in painting, even though it knows also. Oh well, it is in painting actually. So you just select like I want to get rid of this stuff. You condition it with the mask of the stuff you want to get rid of, and it's able to recreate the image. And we have 4 minutes after the time, so that's it. And if there are questions, feel free to ask. Yeah, thanks. Or we should go to lunch, right? Let's go. There are plenty of questions. Yeah.